Hello, and welcome. Let's take a detailed journey to understand the fundamental concept of electric current, breaking down everything you see on this image in simple, easy-to-follow terms. At its very heart, electric current is simply the movement or flow of electric charge. While this charge can be various particles, in the everyday circuits we use, it's almost always the flow of tiny, negatively charged particles called electrons moving through a material, known as a conductor, which is typically a metal wire. To make this abstract idea more concrete, let's use the popular analogy of water flowing through a pipe. Imagine the wire is the pipe, and the electrons are the water molecules flowing within it. The rate at which this water flows past a certain point is what we would call the current. Now, to put a number on this flow, we use the basic formula you see here, I equals Q divided by T. Let's break that down. I is the symbol for current, and its strength is measured in a unit called amperes, often shortened to amps and abbreviated as A. So when you hear about a 1 amp charger, it's describing the rate of charge flow. Q stands for the amount of charge itself, which is measured in a unit called coulombs, abbreviated C. 1 coulomb is a very large number of electrons, about 6.24 quintillion of them. And finally, T represents the time over which we measure this flow, which must be in seconds for the formula to work correctly. So, the formula is telling us that the current in amperes is equal to how many coulombs of charge pass a point in 1 second. To make a current flow, we need a few more things, which brings us to the other units listed. Voltage, represented by V and measured in volts, is the electrical pressure or push that forces the electrons to move. Think of it as the pump that creates pressure to push water through the pipe. In our diagrams, the battery provides the voltage. Resistance, represented by R and measured in ohms, with the Greek omega symbol omega, is the opposition or friction to the flow of current. It's like a narrow or clogged section of the pipe that makes it harder for water to pass. In the diagrams, the zigzag symbol represents a resistor, a component designed to have a specific amount of resistance. Now, let's tackle what is often the most confusing part for beginners, the direction of current. Looking at the detailed diagram on the bottom right, you'll see two different flows indicated. The first is electron flow, shown by the red path. Since electrons are negatively charged, they are repelled by the negative terminal of the battery and attracted to the positive terminal. So, they physically flow from negative to positive. This is the actual, physical direction of the charge movement. However, long before electrons were discovered, scientists, including Benjamin Franklin, made a guess and defined current as the flow of positive charge. This historical definition, which flows from the positive terminal, through the circuit, and back to the negative terminal, is called conventional current, shown here by the blue path. Even though we now know it's not what physically happens, this convention is still the standard used in all electrical engineering and circuit diagrams today, like the one at the top right where the arrow indicates conventional current. So, when you analyze a circuit, you will always use the conventional flow from positive to negative. Finally, it's useful to know the two main types of current. The kind produced by a battery, which flows steadily in one single direction, is called direct current, or DC. This is what powers your phone and laptop. The other type is alternating current, or AC, which is what comes out of your wall sockets. In AC, the current rapidly changes its direction, flowing back and forth many times per second. By understanding these core ideas, what current is, how we measure it, what pushes it, what resists it, and the crucial difference between conventional and electron flow, you have built a solid foundation for exploring the exciting world of electronics.